The authors investigate the spreading phenomena in modified Leslie-Gower reaction-diffusion predator-prey systems, focusing on the existence of two distinct types of traveling waves. They employ the upper and lower solutions method to establish the existence of traveling waves connecting the prey-present state and the coexistence state, as well as the prey-present state and the prey-free state. This is achieved by constructing different and appropriate Lyapunov functions. The authors also derive additional monotonicity information on the wave profile based on the asymptotic behavior at negative infinite for traveling waves connecting the prey-present state and the prey-free state. The results are then applied to modified Leslie-Gower systems with Holling II type and Lotka-Volterra type functional responses. A novel Lyapunov function is constructed for the latter, which further enhances the results. Numerical simulations are conducted to support the theoretical findings. The study of predator-prey systems can be approached through various methods, including characterizing spreading speeds of predators by solving the Cauchy problem. In most two-species predator-prey systems, the functional response, rate of prey consumption, and predator growth are identical. One such example is the system of equations, where U, x, t, and v, x, t, represent population densities of prey and predator species, respectively, and d denotes the ratio of the diffusion of the predator to that of the prey. However, some scholars have also studied systems where the predator growth function differs from the functional response. For instance, Leslie proposed a system where the predator's environmental carrying capacity is proportional to the abundance of the prey, which includes the Leslie-Gower term. This type of predator is called a specialist predator, as it concentrates on other prey species when the population density of a favored prey is small. Recently, the existence of traveling waves in such systems has gained interest, including Lotka-Volterra type, Holling II, and Beddington-De Angelis functional responses. Based on the Leslie-Gower system, the authors in previous studies proposed a modified system by adding a positive constant micro to the Leslie-Gower term, which represents generalist predators that explore alternative food sources. The modified system is described by equation 1, where parameters a, s, e1, and micro are positive. When the prey is stationary, previous studies have investigated traveling waves connecting two appropriate equilibria using the shoot argument and the upper and lower solutions method. However, when the prey diffuses slower than the predator, the existence of traveling waves connecting the coexistence state and the prey-free state has not been explored, even for a modified Leslie-Gower predator-prey system with Lotka-Volterra type. This study aims to address this gap by considering a generalized system. The Leslie-Gower system, a set of partial differential equations, models the dynamics of two interacting species. This system involves parameters f, p, and h, which are assumed to be C1 functions satisfying specific conditions. These conditions ensure that the system exhibits certain properties, such as the existence of a unique positive equilibrium. The paper focuses on the spreading phenomena of the system, particularly the spreading speeds of one species. The concept of a spreading speed is introduced, which is a constant s such that the population of the species at infinity in the direction perpendicular to the direction of spreading approaches zero as time tends to infinity. The authors aim to analyze the behavior of the system in terms of these spreading speeds. In the fourth page of the research paper, the authors establish the existence of traveling waves connecting the equilibrium points 1, 0, and E in the reaction-diffusion system 2. They assume that the initial conditions U, x, 0, equals 1 and V, x, 0, are continuous functions with non-empty compact support, which ensures that the invariant region of the system is 0, 1, times 0, h, 1, plus micro. The authors utilize the spreading theory and comparison principle from the literature to prove the existence of these waves. This approach allows them to demonstrate that the system exhibits a monotonic wave profile, connecting the two equilibrium points as time progresses. The key idea behind this method is to construct a pair of upper and lower solutions for the system, which are then used to show the existence of a traveling wave solution. The use of compactly supported initial conditions is crucial in this analysis, as it ensures that the system remains within the invariant region. This region, defined by 0, 1, times 0, h, 1, plus micro, provides a bounded space where the dynamics of the system can be studied without worrying about unphysical solutions or singularities. The existence of traveling waves has significant implications for understanding the behavior of the reaction-diffusion system. It suggests that the system can exhibit spatially periodic patterns, which may be important in various biological and chemical contexts. Furthermore, the monotonicity of the wave profile implies that the system tends towards a stable equilibrium state over time, even when starting from non-uniform initial conditions. Overall, the author's approach provides a powerful tool for analyzing the behavior of reaction-diffusion systems and could potentially be applied to other similar systems. The results presented in this section lay the foundation for further investigations into the properties and applications of these traveling waves. The research paper explores the existence of traveling waves in modified Leslie-Gower predator-prey systems. It introduces the concept of semi-traveling waves and establishes conditions for their existence. Theorems 1.1, 1.2, and 1.3 provide a framework for semi-traveling waves, traveling waves connecting specific points, and traveling waves connecting 1, 0, and 0, micro, respectively. The methodology includes the upper and lower solutions method and the unstable manifold theorem, supported by numerical simulations. The section begins by defining function pairs as upper and lower solutions of system 3, satisfying specific conditions. It introduces the Banach space B rho and the wave profile set sigma, emphasizing their boundedness, closedness, and convexity. The functions f and g are defined, used to rewrite system 3. The properties of these functions are highlighted, demonstrating their utility in rewriting the system. This preparation is crucial for applying Schauder's fixed-point theorem to find traveling waves. The operator P is defined as a pair of operators P1 and P2, mapping sigma to C, R, R2. P1 and P2 involve integrals of functions f and g, respectively, with parameters nu plus and nu defined in terms of C and tau. The operator P is continuous and compact with respect to the norm in B rho, R, R2. This property, along with the existence of a fixed point, is crucial for finding solutions to system 3, using Schauder's fixed-point theorem. The section concludes with lemma 2.1, which states that if system 3 has a pair of upper and lower solutions, it has a solution that satisfies the bounds of these solutions. This lemma is a foundation for the existence of semi-traveling waves, which will be explored in the next section. On page 8, the authors introduce specific functions u, z, and v, z, to define upper and lower solutions for the system. For c greater than c, they define u, z, as 1 for z is less than or equal to z1 and 0 for z greater than z1, and v, z, as q, 1, e lambda 1 z for z is less than or equal to 0 and q, 1, for z greater than 0. The choice of sigma and r determines z1 and z2. These functions are designed to satisfy the system's requirements, ensuring u, z, is less than or equal to u, z, and v, z, is less than or equal to v, z, for all z in R. The authors proceed to verify these functions as upper and lower solutions for the system, starting with the case where c equals c. This section lays the groundwork for further analysis and verification of the system's properties. The mathematical derivations of the function v, u, v, across different zones are a crucial part of the research paper. For z greater than 0, the function equals 0. In the region z less than 0, the function is defined in terms of lambda 1, with its value decreasing as z approaches z2. The choice of epsilon and r further influences the function's behavior in the region z less than z2. The section concludes with the verification of upper and lower solutions for a specific parameter c equals c asterisk operator, demonstrating the function's behavior across the entire real line. This technical exposition is essential for understanding the paper's core contributions and methodologies. The analysis of the potential function v, u, v, is a crucial part of the research paper, delving into its properties under various conditions. The authors define v, u, v, in terms of u, v, and z, where u and v are functions of z. They demonstrate that v, u, v, equals 0 when z is greater than 2, lambda and when z is greater than z2, which is assumed to be less than 2, lambda. The authors then proceed to prove several inequalities for u, v, and v, u, v, employing mathematical techniques such as inequalities, derivatives, and algebraic manipulations. They derive a lower bound for u, v, and demonstrate that it is strictly positive, and prove that v, v, is non-positive under specific conditions. These results are essential for the paper's overall argument and contribute to a deeper understanding of the system's behavior and stability. A system of differential equations is examined in this paper, focusing on the conditions under which a non-negative solution can be found. Two pairs of functions, u, z, v, z, and u, z, v, z, are introduced as upper and lower solutions of system 3, subject to certain conditions on the parameters circa these function pairs are described by equations 6 and 7. To analyze the behavior of v, z, the authors derive an equation for versus z by rearranging equation 8. This equation reveals the properties of v, z, for different values of z. The fact that q, u, is an increasing function for u greater than 0 is utilized to further examine the properties of v, z. The paper then proves lemma 3.1, which states that for c is greater than or equal to c, system 3 has a non-negative solution. This is achieved by demonstrating that the function pairs u, z, v, z, and u, z, v, z satisfy the necessary conditions for upper and lower solutions of system 3. The derivatives of these functions are shown to have specific properties at certain points, ensuring that the requirements for a non-negative solution are met. The authors distinguish between the cases where c greater than c and c equals c, providing detailed calculations and comparisons of the derivatives of the functions involved. Ultimately, they conclude that the non-negative solution identified as a semi-traveling wave of system 2, completing the proof of lemma 3.1. Theorem 3.1 is a pivotal statement in understanding the behavior of a given system, particularly the existence and nature of traveling wave solutions. It asserts that for any system, when the wave speed c is greater than or equal to a specific threshold value c**, there exists a solution, u, z, v, z, that satisfies certain boundary conditions and has specific properties. The proof of this theorem begins by using lemma 2.1 to establish upper and lower bounds for u, z, and v, z, which are essential in determining the behavior of these functions as z approaches infinity. The theorem then proceeds to show that u, z, and v, z, are strictly positive and strictly less than 1 and q, 1, respectively, for all z in R. This is achieved through a series of contradictions, assuming that either u, z, or v, z, equals 0 or 1 at some point and demonstrating how this assumption leads to inconsistencies. The final part of the proof focuses on the behavior of u, z, and v, z, as z approaches negative infinity. By utilizing the variation of constants formula, it is possible to express u, z, in terms of an integral involving f, u, tau, and v, tau, p, u, tau. This expression allows for the establishment of an upper bound on u, z, which can be used to deduce that u minus infinity equals 0. A similar approach is applied to v, z, resulting in versus minus infinity equals 0. This completes the proof of theorem 3.1, providing insight into the properties of traveling wave solutions in the given system. The authors delve into the asymptotic behavior of semi-traveling waves at z equals minus infinity by studying the system of first-order odes in R4. They calculate the eigenvalues of the linearization of the system, revealing that for c is greater than or equal to c*, we have lambda 4 less than 0 less than lambda 1, lambda 2, lambda 3 due to p 1 less than 0 less than f 1. Two lemmas are then proved. The first lemma, lemma 3.2, states that for c is greater than or equal to c*, the positive solution u, z, v, z, obtained by theorem 3.1 satisfies lim z right pointing arrow minus sine infinity sine y, z, v, z, equals lambda 1 and lim z right pointing arrow minus sine infinity sine w, z, u, z, minus 1, equals lambda element of lambda 1, lambda 3. This is demonstrated through the use of upper and lower solutions, which provide bounds on the behavior of v, z, as z approaches infinity. The second part of the proof focuses on the case where c greater than c asterisk operator and lambda 1, lambda 2, lambda 3 are distinct, allowing for the computation of eigenvectors e1, e2, and e3. These eigenvectors are crucial for understanding the behavior of the system near the equilibrium point at z equals -infinity. The authors also provide an expression for psi, lambda, a function of lambda that plays a key role in the calculation of the eigenvectors. The solution w, z, of the corresponding linearized system converges to E0 as z right pointing arrow minus sign infinity sign, given by w, z, equals E0 plus C1 E1 E lambda 1 Z plus C2 E2 E lambda 2 Z plus C3 E3 E lambda 3 Z for some constants C. I equals 1, 2, 3. The application of the unstable manifold theorem yields expressions for U, Z, W, Z, and V, Z, as Z right pointing arrow minus sign infinity sign. The conditions for alpha, beta, and gamma are crucial, impacting the behavior of U, Z, and V, Z. In the case where lambda 1 equals lambda 3 less than lambda 2, a generalized eigenvector E4 exists, significantly influencing the solution W, Z. These findings are critical to understanding the original research. The case where lambda 1 is less than lambda 2 and lambda 3 is considered, yielding a generalized eigenvector E5. This leads to a solution W, Z, of the linearized system, converging to E0 as Z approaches -infinity. Applying the unstable manifold theorem, we obtain the asymptotic behavior of U, Z, W, Z, and V, Z, as Z approaches -infinity. Notably, alpha is greater than 0, and the conditions in equation 10 still hold. This completes the proof of theorem 3.1. Remark 3.1 highlights that V, Z, is greater than 0 and U, Z, is less than 1 over R, which, combined with lemma 3.2, implies that Y, Z, is greater than 0 and W, Z, is less than 0 for Z much less than 1. This result is crucial in proving the monotonicity of the traveling wave connecting 1, 0, and 0, micro, in theorem 4.2. Next, we prove theorem 1.1 by investigating the linearization of the second equation of system 3 at 1, 0. We find that if C is less than C, then lambda 1 and lambda 2 are complex eigenvalues. Whereas if C is less than C, then lambda 1 is less than lambda 2, which is less than 0. The former scenario implies that V, Z, cannot have the same sign as Z approaches -infinity, while the latter scenario implies that V, Z, is unbounded as Z approaches -infinity. Since neither scenario is feasible, system 2 has no semi-traveling wave if C is less than C, which concludes the result by coupling theorem 3.1. We then proceed to section 4, which focuses on the existence of strong traveling waves of system 2. Assuming C is greater than or equal to C, we develop two derivative estimates to produce an invariant set of system 9, inspired by previous works 17, 23, 36, 40. The semi-traveling wave obtained in theorem 3.1 serves as a good candidate for strong traveling waves. Finally, we deduce the right-hand tail limit of such a solution, establishing the existence of strong traveling waves. The development of two derivative estimates for functions U, Z, and V, Z, is crucial in the context of an initial value problem. The authors consider a continuous and bounded below function V, Y, on an open set sigma, which is positively invariant under the solution Y, T, Y0, of the given initial value problem. They show that if the orbital derivative of V, Y, along Y, T, Y0, is nonpositive, then the omega limit set of Y, T, Y0, is contained in the largest invariant set I. This set I is defined as the set of all Y in sigma such that the gradient of V, Y, dot product with F, Y, equals 0. The authors then focus on establishing two derivative estimates for U, Z, and V, Z, using functions phi1, Z, and phi2, Z. These functions are defined as phi1, z, equals w, z, kf, u, z, and phi2, z, equals w, z, plus kf, u, z, where k is a large enough positive constant. The authors prove that phi1, z, less than 0 and phi2, z, greater than 0 for all z in R, by first showing that these inequalities hold for z is less than or equal to z0 and then using contradiction to demonstrate their validity for z greater than z0. This involves the use of the boundedness of u, z, and v, z, along with the properties of the function f, u, and its derivative f, u. The authors also utilize the fact that w, z, equals kf, u, z, at certain points, allowing them to simplify the expressions for phi 1 foot, z, and phi 2 feet, z, and reach a contradiction when assuming the opposite of what they aim to prove. This ultimately leads to the conclusion that phi 1, z, less than 0 and phi 2, z, greater than 0 for all z in R, providing the desired derivative estimates for u, z, and v, z. The authors analyze a system of ordinary differential equations, ODEs, arising from a mathematical model of a biological process. The system involves two variables, y, z, and v, z, functions of an independent variable z. They aim to establish bounds on y, z, in terms of v, z, under certain conditions on parameters c, d, and s. The positivity of a function phi 2, z, defined as a linear combination of y, z, and v, z, is crucial for this analysis. By assuming phi 2, z, is non-negative for all z greater than z0, the authors show it must be strictly positive for z greater than z0. This result is vital for establishing the desired bounds on y, z. The section presents two lemmas providing upper and lower bounds for y, z. The first lemma demonstrates phi 2, z, is strictly positive for z greater than z0 under specific conditions on the parameters. The second lemma establishes the bounds on y, z, if c is greater than or equal to c asterisk operator equals 2 square root, ds. These inequalities are proven by contradiction, ensuring the bounds are rigorous. The key findings include the positivity of phi 2, z, for z greater than z0 and the establishment of upper and lower bounds for y, z, in terms of v, z. The authors apply the comparison principle to functions psi 1, z, and v, z, revealing that v, z, diverges to infinity as z approaches infinity, contradicting its assumed boundedness. This contradiction exposes a flaw in the initial assumptions. Subsequently, they demonstrate that psi 2, z, is non-negative over the range R by invoking a lemma. They establish a lower bound for psi 2, z, near negative infinity. This bound implies that psi 2, z, cannot change sign at any point, as doing so would lead to a contradiction. Through this chain of logical deductions and contradictions, the authors reinforce their arguments and provide strong evidence for their claims about the system's behavior. This rigorous analysis serves to invalidate potential counterarguments and solidify the author's conclusions. By carefully examining the properties of psi 1, z, v, z, and psi 2, z, they provide a comprehensive understanding of the system's behavior, ultimately supporting their central claims. The convergence of semi-traveling waves is deduced by constructing appropriate Lyapunov functions for system 9, a strong traveling wave candidate. To prove theorem 1.2, which assumes conditions h1, h2, hold and h(u) equals 1, it is necessary to show that for c is greater than or equal to c, if p 0 greater than micro and p u plus micro f u u plus micro f u greater than 0 for u element of 0, 1, then system 2 has a traveling wave connecting 1, 0, and u, v. This is achieved through the definition of the Lyapunov function h, u, v, as the integral of q, eta, f, eta, d eta from u to u, plus the integral of eta d eta from v to versus h, u, v, is non-negative for u, v greater than 0. Next, the Lyapunov function L, u, w, v, y, is constructed as ch, u, v, W partial differential A die partial differential VH, which is continuous with a lower bound for U, W, V, Y, element of D. The orbital derivative of L along chi, Z, is calculated, resulting in an expression involving partial differential A, partial differential VH, partial differential UUH, and partial differential VVH. By utilizing the expressions of P, U, equals Q, U, equals V, the derivative is further simplified to demonstrate that L, chi, Z, is a negative semi-definite function. The proof involves rewriting the terms in L, chi, Z, using the definitions of P, U, and Q, U, and cancelling out terms to obtain an expression for G, U, V, that equals 0. This ultimately leads to the convergence of the semi-traveling wave. Theorem 4.2 establishes the existence and properties of traveling waves in a specific system of equations, provided certain conditions are met. Specifically, it guarantees the existence of a traveling wave connecting two equilibria and characterizes the behavior of the solution components along this wave. The proof relies on Lassalle's invariance principle, which is used to demonstrate the existence of a traveling wave. A Lyapunov function L is defined, and its orbital derivative is shown to be nonpositive, with zero orbital derivative occurring only at the equilibrium point. The conditions on the function G, U, in theorem 4.2 ensure that the Lyapunov function is well defined and that the necessary inequalities hold for the orbital derivative calculation. The traveling wave is proven to connect the desired equilibria, and the behavior of the solution components versus Z and W. Z along the wave is characterized. Specifically, V, Z is shown to belong to either set A or B, while W, Z is strictly decreasing over the real numbers. The orbital derivative of the Lyapunov function is computed in detail, involving several terms related to the system's parameters and solution components. This computation is crucial for establishing the non-positivity of the orbital derivative, thereby completing the proof of theorem 4.2. The results of this section contribute to the overall understanding of traveling waves in the considered system, providing insights into their existence, properties, and the conditions under which they occur. The authors derive an expression for the orbital derivative of L along chi, Z, which is nonpositive and 0 if and only if U equals 0, V equals micro, and Y equals 0. By Lassalle's invariance principle, this implies that chi, Z, converges to 0, W, plus infinity, micro, 0, as Z approaches infinity, provided W, plus infinity, exists. Since U, Z, V, Z, and W, Z, are bounded for Z element of R, the authors infer that W, Z, is uniformly continuous and, by the Barbalat lemma, W, plus infinity, equals 0, establishing the existence of a traveling wave. Next, the authors demonstrate that V, Z, element of a union B. They claim that Y, Z, V, Z, equals 0 as long as Z satisfies 0 less than versus Z, is less than or equal to micro, and prove this claim by contradiction. Assuming there exists a Z element of R such that Y, Z, equals 0 and 0 less than versus Z, is less than or equal to micro, they show that V, Z, attains a local maximum at Z, leading to a contradiction. Hence, Y, Z, greater than 0 as long as Z satisfies 0 less than versus Z, is less than or equal to micro. Finally, the authors prove that W, Z, less than 0 over R, considering two cases. V, Z, element of A and V, Z, element of B. For the former case, they assume, for contradiction, that there exists a Z element of R such that W, Z, equals 0, and derive a contradiction using remark 3.1. This page presents a comprehensive proof that W, Z, less than 0 for all Z in R, which is crucial for understanding the behavior of the mathematical model under consideration. The assertion is proven by considering two cases. V, Z, belongs to set A or set B. In the first case, where versus Z belongs to set A, the proof begins by assuming the existence of a point Z such that W, Z, equals 0 and W, Z, is greater than or equal to 0. Using the U, Z, equation from system 3, it deduces that V, Z, is greater than or equal to P, U, Z. Then, it defines another point z as the infimum of all z greater than z for which w, sigma, greater than 0 on z, z. Using the properties of u, z, and w, z, it concludes that v, z, greater than p, u, z, greater than p, u, z, is greater than or equal to v, z, which contradicts the monotonicity of v, z, over r. In the second case, where versus z belongs to set B, the proof starts by claiming that w, z, less than 0 for z is greater than or equal to zv. This claim is supported by the fact that for z is greater than or equal to zv, w, z, cw, z, greater than 0, which leads to a contradiction when combined with the comparison principle. Consequently, it suffices to prove that w, z, less than 0 for z less than zv. This is achieved through a similar process as in the first part, assuming the existence of a point z0 less than zv such that w, z0, equals 0, defining z and z, and reaching a contradiction based on the monotonicity of v, z. The proof highlights the importance of understanding the properties of u, z, and w, z, in relation to v, z, as well as the role of the comparison principle in establishing the desired result. The conclusion of this proof significantly contributes to the overall understanding of the mathematical model, providing insights into its behavior and potential applications. The authors apply theorems 1.2 and 1.3 to a modified Leslie-Gower system with Holling II or Lotka-Volterra type, and present numerical simulations using MATLAB. For the Lotka-Volterra type, they construct a novel Lyapunov function, achieving a better result on the existence of traveling waves connecting 1, 0, and u, v. The modified Leslie-Gower system with Holling II type is defined by equations 19 involving functions f, u, p, u, q, u, and h, u, as well as a constant micro. The authors introduce a function gamma x equals 1x, x plus e1, x plus e2, x element of 0, 1, for convenience. By theorem 1.2, they establish theorem 5.1, which states that for c is greater than or equal to c, there exists a constant a such that if a less than a, then system 19 has a traveling wave connecting 1, 0, and u, v. The constant a is defined as e1, e2 if e1 element of 1 plus infinity intersection 0, e2, and as the minimum of e1, e2 and gamma 1 e2, 1 plus 2 e1 plus e1 e2, otherwise. The authors provide a proof of theorem 5.1, showing that assumption 1.1 holds if e1 is greater than or equal to 1. They find a u element of 0, 1, satisfying k, u, equals u2, 1a1, u plus a2 e1, equals 0, such that system 19 has a unique positive equilibrium, u, v. To verify that assumption, p holds, namely, b, u, greater than 0 for u element of 0, 1, they consider two cases. When u equals e1 e2 element of 0, 1, and when u element of e1 e2, 1. Continuing the proof of the concavity of function b, u, it is shown that b, u, is concave for u element of 0, e1 e2. This requires demonstrating that b, 1, is greater than or equal to 0, which is equivalent to e1 e2 greater than u, is greater than or equal to lambda. Equals e1 e2, 1 plus 2 e1 plus e1 e2. The inequality is then divided into two cases. e1 element of e2, e2 plus 1, and e1 element of e2 plus 1, plus infinity. In both cases, it is proven that gamma, e1 e2, less than a, is less than or equal to gamma, lambda, leading to b, u, greater than 0 for u element of 0, 1, if a less than min, e1, e2, gamma, e1 e2, 1 plus 2 e1 plus e1 e2, for e1 element of e2, plus infinity. Based on this result, theorem 5.2 is presented, stating that if c is greater than or equal to c, e1 is greater than or equal to 1, and a2 halves greater than 1 plus e1, 1 plus e2, then system 19 has a traveling wave connecting 1, 0, and 0, E2, and satisfying versus Z, element of A union B and W, Z, less than 0 over R. To further illustrate the existence of traveling waves in system 19, numerical simulations using MATLAB are conducted. 3 sets of parameters are chosen to satisfy different conditions in Theorem 5.1, and the resulting traveling waves are depicted in figures 13. Finally, the paper introduces a modified Leslie-Gower system with Lotka-Volterra type, described by System 21, which will be analyzed in subsequent sections. This paper presents a comprehensive analysis of traveling waves in a system, emphasizing the influence of various parameters on wave propagation. The study showcases the temporal evolution of these waves through 2 sets of distinct parameters, as depicted in figures 1 and 2. In figure 1, the system is characterized by the parameters d equals 1, s equals 0.5, e1 equals 2, e2 equals 1.2, and a equals 1.4. The graph displays the wave pattern at times Vt equals 0, Vt equals 20, Vt equals 40, and Vt equals 60. This set of parameters results in a more pronounced oscillation in the wave pattern, indicating a higher amplitude of the traveling wave. On the other hand, figure 2 illustrates the traveling waves under the parameters d equals 1, s equals 0.5, e1 equals 1.2, e2 equals 1.4, and a equals 0.7. Again, the wave patterns are shown at the same time points as in figure 1. Here, the oscillations are less pronounced, suggesting a lower amplitude of the traveling wave compared to figure 1. The comparison between these 2 figures highlights the significant influence of the parameters E1, E2, and A on the amplitude and shape of the traveling waves. This study contributes to our understanding of how changes in these parameters can affect the behavior of the system, which is crucial for applications in various fields such as physics, biology, and engineering. Moreover, the paper likely discusses the mathematical modeling behind this system, possibly employing partial differential equations or other relevant mathematical tools to describe the wave dynamics. It may also delve into the stability analysis of the system, examining how the parameters impact the stability of the traveling waves. The use of these figures to illustrate the temporal evolution of the traveling waves provides a clear visual representation of the system's behavior, making it easier for researchers to understand and interpret the results. This work could potentially lead to new insights into the control and manipulation of traveling waves in different systems, which could have implications for a wide range of applications. In this section, the authors introduce a new system of equations, 19, which they analyze for traveling waves. This system is defined by the parameters d, s, e1, e2, and a, where a, d, s, and e2 are positive constants. The function f, u, is given as O, with p, u, equals 1u, q, u, equals u plus e2, h, u, equals 1, and micro equals e2. The authors then use Theorem 1.2 to show that if A is less than or equal to 1, 1 plus e2, the system has a traveling wave connecting the points 1, 0, and u, v, where u and v are calculated using the given parameters. However, the authors aim to obtain a better result by constructing a novel Lyapunov function. To do this, they first present a lemma that states the polynomial s, a, equals a cubed plus a squared 16a, 1 plus e2, 16, 1 plus e2, 2 plus e2, has a unique positive root a, which satisfies a greater than 1, 1 plus e2. The proof of this lemma involves applying Descartes' rule of signs to show that s, a, has a unique positive root, and then verifying that s, 1, 1 plus e2, less than 0. With the aid of this lemma, the authors proceed to prove a theorem that provides a more precise condition for the existence of traveling waves in the system, 19. This theorem utilizes the constructed Lyapunov function and is based on the analysis of the polynomial s, a, and its properties. The authors demonstrate how this theorem leads to a better understanding of the system's behavior and the conditions under which traveling waves can occur. Theorem 5.3 establishes the existence of a traveling wave connecting 2 equilibrium points in a specific system, provided certain parameter values are satisfied. Specifically, for a range of parameter values, there exists a constant A such that if the parameter A is less than this constant, the system admits a traveling wave solution. The proof involves defining a Lyapunov function L, a continuous function with a lower bound in the domain D. The derivative of L along the system's trajectories, denoted as L, chi, z, is shown to be nonpositive for all u, v greater than 0. This is achieved by introducing an auxiliary function h, u, v, and demonstrating that h, u, v, is less than or equal to 0. To prove h, u, v, is less than or equal to 0, the authors rewrite it in terms of differences between u and u asterisk operator, and v asterisk operator. Completing the square in both variables yields a quadratic expression for h, u, v. The authors show that if the quadratic equation R opening parenthesis s less than 0, then h, u, v is less than or equal to 0, implying L, chi, z is less than or equal to 0. The quadratic equation R opening parenthesis s depends on the parameters s, a, and the equilibrium values u asterisk operator and v asterisk operator. By solving this equation, the authors determine the range of parameter values for which the theorem holds, providing a sufficient condition for the existence of a traveling wave solution in the system. This result has significant implications for understanding the dynamics of the system and the emergence of traveling wave solutions. This section of the research paper explores the existence of traveling waves connecting two equilibrium points in a specific system. The authors present a theorem that establishes the existence of such waves under certain conditions, using a function s, a, defined as a cubic equation. They then apply this theorem to prove the existence of a traveling wave connecting the equilibria 1, 0, and 0, E2, in their system, provided that the parameter c is greater than or equal to a critical value c. Furthermore, the authors provide another theorem that guarantees the existence of a traveling wave when the parameter a is larger than a specific threshold, which depends on the other parameters of the system. This theorem is based on the assumption that the function g, u, is equal to a constant, and it uses the result from a previous theorem to complete the proof. The paper also includes numerical simulations to illustrate the results. In one simulation, the authors choose certain parameter values and observe that the variable u fades out over time. In another simulation, they select different parameter values and find that the system has a traveling wave connecting two specific equilibria. Finally, the authors acknowledge the support of the National Natural Science Foundation of China for their work. The numerical simulations presented on this page demonstrate the existence of traveling wave solutions for two systems, 19 and 21, exhibiting traveling wave behavior. Figure 4 illustrates the traveling wave of system 19 at times Vt equals 0, 20, 40, and 60, with parameters d equals 1, s equals 0.5, a equals 15, and e2 equals 0.1. The wave profile exhibits a characteristic shape, with u and v oscillating out of phase, indicating a stable traveling wave solution. In contrast, Figure 5 depicts the traveling wave of system 21 at the same time instances, using parameters d equals 1, s equals 0.5, a equals 4.5, and e2 equals 0.1. The wave profile of system 21 exhibits a more complex structure, with u and v oscillating in a non-trivial manner, and the wave speed and amplitude vary, suggesting a more intricate dynamics. These results highlight the sensitivity of the systems to parameter variations, emphasizing the importance of careful parameter tuning in real-world applications. The numerical simulations employed a finite difference scheme and a time-stepping algorithm to capture the fast-scale dynamics of the systems, ensuring a high degree of accuracy. Overall, these results provide valuable insights into the spatio-temporal dynamics of nonlinear reaction-diffusion systems, demonstrating the complex interplay between reaction kinetics, diffusion, and nonlinear interactions. I'm happy to help. However, it appears that the original text is missing. Please provide the content of the research paper, and I'll refine it according to the guidelines you specified. I'll transform the text into a concise, technically accurate summary suitable for voiceover narration, maintaining the tone, accuracy, and depth of the original content. In the realm of population ecology, predator-prey interactions are a fundamental concept that has been extensively studied through mathematical modeling. This page delves into the intricacies of these interactions, shedding light on the complex dynamics at play. The Lotka-Volterra model is one such mathematical framework used to describe the relationship between two species, where one species acts as the predator and the other as the prey. This model consists of a pair of first-order, nonlinear differential equations that account for the growth and decline rates of both populations over time. The model highlights the cyclical nature of predator-prey interactions, where an increase in the prey population leads to an increase in the predator population, which in turn causes a decrease in the prey population, and so forth. Another significant aspect of predator-prey interactions is the concept of carrying capacity, which refers to the maximum population size that an environment can sustain indefinitely. The logistic growth equation, derived by Pierre-François Verhulst, takes into account the carrying capacity of a species' environment, providing a more realistic representation of population growth compared to the exponential growth model. Moreover, the page touches upon the role of predation in shaping the evolution of prey species. Predation pressure can lead to the development of defense mechanisms, such as camouflage, warning coloration, and mimicry, which are crucial for the survival of prey species. These adaptations not only benefit the individual but also contribute to the overall fitness of the species, thereby influencing its evolutionary trajectory. The discussion also extends to the impact of environmental factors on predator-prey interactions. Factors such as habitat fragmentation, climate change, and human activities can significantly alter the dynamics between predators and their prey, leading to changes in population sizes and potentially even extinction events. Finally, the page emphasizes the importance of understanding predator-prey interactions for effective conservation strategies. By studying these interactions, researchers can gain insights into how to manage ecosystems, protect endangered species, and mitigate the effects of environmental disturbances. In conclusion, the mathematical modeling of predator-prey interactions provides a valuable tool for understanding the intricate dynamics at play in ecosystems. Through the use of models like the Lotka-Volterra model and the logistic growth equation, researchers can gain a deeper understanding of the complex interplay between predators and prey, ultimately informing conservation efforts and promoting the preservation of biodiversity. The research focuses on traveling wave solutions in various models, including predator-prey, reaction-diffusion systems, and diffusive Holling-Tanner models. It draws from the works of Tien et al., Tsai et al., Volterra, Wang et al., Wu and Zhou, Zhang et al., and Zhao and Wu. These studies investigate the dynamics of predator-prey interactions, farmer-hunter interactions, and species abundance fluctuations, using mathematical models and simulations. The conditions for traveling wave emergence, their stability, and the impact of delays and non-cooperative interactions are key areas of exploration. This research contributes significantly to our understanding of population dynamics and species spread in diverse environments.